First of all, let me just say a little bit more about complex manifolds. So remember that I decomposed the de Rham complex using an almost complex structure. And when you complexify all of the things involved, then the de Rham complex looks like this. These are the various so-called types of forms in question. So this is pronounced forms of type 1,1. This is forms of type 0,2, and so on. And a priori, when you look at the de Rham complex, you find that, well, you get an arrow going from there to there and there to there, and these have names. That's D and D bar. But then here, there are various arrows, and in order to be a complex manifold, rather than an almost complex manifold, you insist that this arrow, which is actually a homomorphism, be 0. Now, as soon as this one's 0, and its complex conjugate, which is that one, you're left with a much more familiar sort of pattern that you find in any book on complex analysis. So when you look in, for example, Ronnie Wells's book on whatever it's called, then you'll find a pattern which looks like this, and then continues until you run out of manifold. Okay, and in particular, you notice that the kernel of this thing, which are the holomorphic functions, this is the Cauchy-Riemann operator. These are the Cauchy-Riemann equations encoded nicely, gives rise to a nice complex which goes down the bottom of this diagram, dot, 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 dot. And that one has a name, and that one is called the Dolbeau complex. And so this is just to connect up what I was saying with the rest of the world. This is called the Dolbeau complex, as opposed to the de Rham complex, which is the thing we started with. And the Dolbeau complex has this nice property just like the Dolbeau complex, just like the de Rham complex. First of all, it's a complex because I've gotten rid of this problem. There's a problem. Used to be a problem homomorphism going from there to there, so that there's no way that this thing could be 0 if it's not being anyway. So if there's the only possible arrow going from here to here is this one, then you can see that this is actually a complex. But also, this Dolbeau complex is locally exact. Right? So just like the de Rham complex, that's locally exact. That's called the Poincaré lemma. This one is locally exact. That's called the Dolbeau lemma. Okay? But it's a different argument because it's not just, okay, but a similar argument, some sort of integral formula to go back. All right, so that's just to connect it up with usual complex analysis that you find in books. Okay, now the next thing I was talking about was about the killing operator in R3. And we decided that actually the solutions of the killing operator were a finite dimensional vector space of dimension 6. So there was a 6-dimensional vector space, and then there were various bundles. Right, so but in order to find the 6-dimensional vector space, we'd done this trick of prolongation. The trick of prolongation led us to another bundle, which I called E. And this is a trick which works in any dimensions. Perhaps the neatest way of saying it is that it's just things in E are a pair consisting of a 1 form and a 2 form. Okay, so a gadget in here, a section of this bundle looks exactly like this, where I've called this thing sigma and this thing mu. This one is just a 1 form. This one is skew. So this bundle, by the way, let me just compute its rank. So the rank of this bundle is n for that. The rank is just how many dimensions it's got in each fiber. Okay, so this is n for that, and this is n times n minus 1 over 2. And altogether, That's n plus 1 over 2 when you add them up. You can probably all do, I'm not very good at arithmetic, but I've done this before. So this is, for example, when n is equal to 3, this is 3 times 4 over 2, which is 6. That's where this 6 came from. And the point is that when you're looking at solutions of the killing operator, you can encode them into the following. What you do is you define a differential operator on this pair rather than just on sigma itself. And you end up with this in the top position, so that if that is equal to 0, that is saying that the derivative here is skew, which is exactly the same as saying its symmetric part is equal to 0. And you conclude, as a sort of auxiliary equation that you can either put in or not as your mood takes you, that that must also be 0. So what you do is you define this differential operator like that. And, this is a really nice differential operator because what it's done is it's taken these things here and it tells you what their derivatives in all possible directions. There are no symmetry signs here or skew signs or anything like that. In the first line is telling you what all of the partial derivatives of sigma are in all possible directions. And similarly here. I should say right away that this is a connection. Like so. Rather confusingly, I'll call this one by exactly the same letter, but I mean this is a connection on a vector bundle E. So before writing any more here, if you're taking notes, leave a little bit of space, and I'll just give you a very, very brief rundown of the sort of gadgets that are involved in talking about differential geometry in this context. So it's basically a bunch of key words. The problem with differential geometry is if you try and read a book on differential geometry, you'll find first of all, it's about that thick. And secondly, you get the impression that almost nothing is happening because it's just definition after definition after definition. Propositions which are all more or less obvious. And you get to the end of the book and you wonder what's actually going on. But it's really, really good, but you have to just persist with it. It's a steep learning curve. But things you come across are vector bundles. And actually, when people first start talking about vector bundles in a book on differential geometry, you'll wonder what's happened to them because always they're talking about the tangent bundle or the cotangent bundle. Now, right away here, you can see I'm actually encountering a bundle which is not a naturally encountered bundle, which is not just the tangent bundle or the cotangent bundle. It's some sort of combination. Okay, so already we're into the realm of actual vector bundles purportedly being a useful thing. Okay, the next thing is connections on vector bundles. Okay, and what I'm writing down here, or beginning to write down, is an example of such a thing. It's a connection on a vector bundle. So let me just make some general remarks over here. Vector bundle. Let's call a vector bundle E. All right, so you've got a manifold, you've got a bundle over it, which means you've got vector spaces going this way and smoothness going that way. So this thing here has its fibers as vector spaces. And a connection is a differential operator. All my differential operators are called nabla. And it goes from E to one forms tensor E. This is just a fancy way of saying that you're allowed to differentiate sections of E in any direction that you like on the base. And I should say here that people often be a lot more pedantic than I am being. For a start, they never just write E here, they write sections of E. So they start decorating their ideas with things like this. Or even, worse, they do that. Or, and so on, right? The notation just gets bigger and bigger and bigger, and nothing is really happening. So when I write this, I'm perfectly at liberty to write a differential operator like this. I don't mean a homomorphism of vector bundles. This is a differential operator. And it satisfies some basic defining principle. The basic defining principle is that actually if you take a section of this thing, let's call it S, that's a section of E, you're allowed to apply this thing, and you multiply it by a function, it satisfies some Leibniz rule, right? So first of all, you get F coming out the front, as if it's just linear, but it's not. It's not linear over the functions at all. You get df tensor S as well. This is a Leibniz rule on a product here, and this is the exterior derivative, which we've already counted. That's something in there. That's in S, a section of E. That's perfectly, it makes perfectly good sense. And this is the sort of characterizing feature of a connection. Right. But the next thing you do after that is you talk about curvature. In the notes, if you look in the notes, this is all in a little tiny box, and it goes vector bundles, connections, torsion, and curvature. Right? So I'm going to suppress torsion for the moment and just talk about curvature. So curvature is what happens when you look at this as a connection and you think, wouldn't it be a good idea to try and mimic the de Rham complex? So in the de Rham complex, the sort of suggestion is that this would actually continue on, and the next thing that you would write down would be two forms tensor E. Right? So if E weren't there, this would be the de Rham complex. And of course, the de Rham exterior differential does indeed satisfy some Leibniz rule like that, so this is entirely reasonable. And sure enough, in line with my convention that all differential operators and connections are called nabla, if you've got a connection between here and here, you get automatically, for free, all the way up, you get what's called the coupled de Rham sequence. It's no longer a complex. And it might be that this composition here, from here to here, is not equal to 0. What happens in general is that this thing here is always a homomorphism of vector bundles, and it's called the curvature. Right, so this homomorphism is called the curvature. Okay, and then you can continue. You don't get any more by continuing. If you just continue this sequence, you find it sort of curvature all the way up. If you compose 3 of them, you get 0. That's the Bianchi identity. But there's no extra information beyond this trivial construction of just curvature. That's all that falls out. Right. Now, why do people do this? They do it because they have in mind the so-called Riemannian context. And that's where you, on your manifold M, you have some structure which is, it's not a complex structure or anything like that. What it is, it's a non-degenerate.
Sorry?
Yeah.
En fait, nabla, you replace U by you replace the bender.
What? So.
Nabla and nabla, the same nabla.
Oh no, I mean, oh yeah, okay. So, this nabla here, although it's the same notation, it's just like when people write the de Rham complex. They write the exterior derivative like this, and then, unless you're being really, really pedantic, everybody writes D for the next one on as well. Right? It's not the same operator. It's going between different bundles. But it's just the same notation. Everybody does that. So that's what I'm doing here. I'm using the same notation for this as this. This one here induces this one here. Right? But, and I'm not even going to tell you how, right? Because there's some things to check. Even if you try and do it in a slick way, there are some things to check. Right? So I'm not going to even try. But you'll see it happening in this really good example here. Right? So this is just a bit of a rave, right? No precision here at all. It's just sort of throwing at you some keywords that you can go and read about in big, thick books. Okay? So this is a homomorphism. If you do it for the de Rham sequence, the de Rham sequence is actually a complex. This composition is 0. Right? And this is actually a trivial case where this is a connection on the trivial bundle. So you don't even see it, and the curvature here is 0 because this composition is 0. But if you do it more generally, this composition is a homomorphism which is not necessarily 0. without further ado, I will just write down my favorite convention for how I would even write this. Right, so what I'm doing is always, I have this convention that I'm writing things out as if I'm doing it in local coordinates, but I'm not really. Right, so what I will be asking was what happens if I do one of these connections, like one, and another one, and then take the skew part. Okay, that's heading into there. So what I'm really asking about is something like this, applied to some section of E. Right? And even in line with having indices written on everything, so I have sort of in mind a local coordinate system in which I'm working. For a general vector bundle, what I would have in mind is a smoothly varying basis with respect to which I'm writing everything out. So I have it in mind, but it's just part of the notation now. Right, so let's say alpha. Right, so alpha is an index which might run from 1 to a million if you have a million-dimensional vector bundle. And this is supposed to be a homomorphism. Right, so this on the left-hand side is a differential operator a priori, but it's not. It's actually a homomorphism. And on the right-hand side, you'll have something which is curvature. Everybody uses R for curvature after Riemann. There's a summation convention involved here. So this is actually a 2 form with coefficients in the endomorphisms of your original bundle, which is why it's got an index like that and contracted. It's just an algebraic tensorial operation on the right-hand side. This is the sort of thing that you have to take away from this part of the discussion. Now, at this point, people often come clean about what they're doing. And what they're really doing is heading towards Riemannian differential geometry. So, Riemannian differential geometry. Right, so Riemannian differential geometry, due to Riemann in the first instance, but developed by heaps of other people, lots of other classical people, like Levi-Civita and people, and just too numerous to mention. Okay, but what Riemannian differential geometry does, it starts with a non-degenerate symmetric form. Usually, it's a positive definite non-degenerate symmetric form, which allows you to measure lengths infinitesimally on your manifold. That's the idea. And everybody calls it G. And because I like to decorate things with indices to tell you where they are, it's actually got 2 lower indices. It's a so-called covariant tensor, and it's symmetric in its indices. And from this gadget, you can generate a connection on the tangent bundle. All right, so this gives rise to that. So this is what will happen over several pages of one of these classical books. And you will find a formula like this, except that this is applied to just vectors, because this is the vector connection on the vector on the tangent bundle. This is applied to vector bundle, and your curvature tensor, well, in this formula, well, it would look like this. Del A, B, minus B, A, X, C is equal to that. Okay, so now we have some gadget which involves just tensor indices. And rather confusingly, perhaps what people do is, rather than they consider this, which is the natural gadget that you have, they tend to pull this index C down, right? So there's this procedure called raising and lowering indices in Riemannian differential geometry, whereby you think of this as an isomorphism between the tangent bundle and the cotangent bundle. And it allows you to write this instead. This is what people call the Riemann curvature tensor. It has various exciting symmetries. It is skew in A and B by definition. Also, because of this properties of this connection here, it's actually skew in C and D as well. And then it has some other properties, like if you interchange AB with CD, it's symmetric. Okay, this is called the Riemann curvature tensor. Now I'm telling you this because if you do this process here of prolongation, and you do it on a Riemannian manifold, you do not get a connection as simple as this. You get a connection involving this Riemann curvature tensor. But it occurs in a really nice way. You can almost guess what to put here. It's minus, right? You want something which is skew in a couple of indices, like that. And then you've got an index A, which has to go somewhere, and CD. So let me just, this is an extra term. This is what you would get if you do this on a Riemannian manifold. Okay, so let me just stop. Right, so that formula, if you just look at how I derived this formula yesterday, you would get to a point where I had to interchange a couple of indices. Right, this here tells you how to interchange indices. Right, if you've got a formula involving indices in this order and you want one in the other order, you just apply this formula. Right, when you do that, you find you get this as a connection. Right, so this connection encodes the solutions of the Killing equation. So let me call it the Killing connection. Right? And then right, so I'm not sure who the Killing connection is due to. Might be due to constant. Right. But it's actually part of all of this is part of a much more general story. But the Killing connection already is extremely useful.
Sorry, the data, you take the Riemann and from GAB you construct.
This is an extra term that you add into this connection when you are starting on a Riemannian manifold.
Using the G, okay.
And you're, so on a Riemannian manifold, you're looking at this equation. Well, the kernel of this operator, where this is the Levi-Civita connection. This has a name. If you start with a metric and you end up with this has a name. It's called the Levi-Civita connection. So if you take this thing, Levi-Civita connection, right, and you look at this equation on a Riemannian manifold, you will find that the appropriate way of studying this equation, for example, its kernel, is exactly by studying this connection with this extra curvature term involved. Let me make two remarks about. Right, first of all, this is in general dimensions. This is in any dimension. You get a tensor with four indices on it. Okay, and a priori you think you've just made the problem worse. After all, you started with a metric. That's something with two indices on it. Here it is. Right. What's the good of producing something like this, even if you took its trace? Right, so suppose I contract this thing, get rid of the AC indices. R, B, C, D. Okay, this is by definition R with just two indices on it, B and D. This has a name. It's called the Ricci tensor. You know, what's the good of producing another tensor if you've already got one? Right. Well, one thing is you can compare these two tensors. It might be, for example, that this thing here is proportional to the metric. Well, that would be a perfectly good imposition as a highly nonlinear equation on your original metric. That's called the Einstein equations, and they govern. And those equations govern general relativity. Even if you extract even weaker information about this, suppose you look at R which is taking another trace. So G, this is my notation for the inverse metric. Okay, this is the inverse metric. This actually gives you a scalar function on the manifold, but it's an invariant scalar function. If its value at one point is 6, right, that's it's not something you can ever change. It's just 6 at that point. If you have another manifold where the scalar curvature is always less than 6, there's no way that these things can be diffeomorphic, isometric. Right? So the advantage of creating these new gadgets from old gadgets is so that you can create things out of them that you can genuinely understand. Like, for example, a scalar valued function on your manifold. This is called the scalar curvature. All right. And one more thing. In the Riemannian setting, this equation has a different interpretation. Let's see, it was mentioned in Francine's talk that if you start with a vector field, you can talk about the flow of that vector field. That gives rise to the notion of Lie derivative. So if you have a vector field, and you have any tensor whatsoever on your manifold, for example, a vector field, another vector field, or for example, or even better in this case, a tensor like this, the metric, you can pull back this metric by that flow, and then you can look at the infinitesimal change if you just flow a tiny, tiny bit. Okay, and that's called the Lie derivative. So the Lie derivative of the metric. Okay, this is a perfectly sensible thing to write down for any tensor, any vector field, but in particular in Riemannian differential geometry, you can do that. And to say that, and I should say right away that this thing is equal to twice that, I think. Right, so I'm going to lower the index with the metric. Okay, so this operator which you write down there, which you're thinking of as a differential operator on this for a fixed, so you're thinking of this as applying this to a vector field, right? Then actually you can view it like this. These two different ways of writing things are, here you've got sort of vector field is fixed, and you're thinking about how it affects a metric. Whereas here you've got a metric that's fixed and giving rise to this connection. And you're thinking about how it affects a vector field. Highly confusing, but what this really is, this thing here is a differential pairing between x and g. So you can think of it as g varying, x fixed, or x fixed and g varying. Anyway, this is true. And so you can see that if you've got something here which is 0, what that means geometrically is that your vector field is giving you an infinitesimal symmetry of your manifold. And last time when we worked out what the solutions of this were in R3, we got the 6-dimensional family, and this corresponded infinitesimally to translations, and this corresponds infinitesimally to rotations. And as you know, those are the general Euclidean motions, right? So Euclidean motions in 3 dimensions, you can just translate, get a 3-dimensional family of freedom, or you can rotate. Rotate is, about some axis, that's 2 degrees of freedom, some angle, that's another 1 degree of freedom. Right, so that 6 has a perfectly good geometric interpretation. Right, now, having said all that, we'll now come back to the Saint-Venant complex. Right, this is this complex, 1864. What's that got to do with all of this? Right, this is a much, much higher viewpoint. We should be able to just see the Saint-Venant complex without any, real work. There's no real work involved here. It's just notation. Right. So, okay, what's going on? Right. First of all, whenever you have a complex, whenever you have a connection, as we do here, you should compute its curvature. So let me do that. Okay, so here's my connection. So I'm just going to copy down this formula here, except I'm going to, yeah.
This part is not symmetric here.
Oh, both sides are symmetric. I mean, if you have a symmetric tensor and you take its Lie derivative, it's still symmetric. So left-hand side is symmetric in A and B. Right-hand side is symmetric in A and B because I've taken the symmetric part. Right, this thing is defined to be, this big thing here is defined to be 1/2 of that way round plus the other way round. So this one is decreed to be symmetric. I've taken the symmetric part. Left-hand side is symmetric because it is. Right, so, okay, so as far as the indices go, it's always a good check. Yeah. Right. Let me write down this connection, and I'll compute its curvature to see that we're getting the right sort of thing. So I'll leave a little bit of a gap here. First, I just write down what the connection is, except I've renamed the indices. Okay, so nothing has happened yet. But I'm going to apply this connection again. Right, so this is the definition without this curvature. Let's do it again. Right, and then you have to keep a fairly clear head as to what's going on here. This B index here, what you're ending up with is something which is in one form's tensor E. E is to do with the indices C and CD. The one forms here are to do with this index B. And I'm doing this again. So the B is a passenger. Right? So I'm going to apply this differential operator, bearing in mind that B isn't really involved. Right? So B just sits there throughout this calculation. Right? So first of all, I differentiate the top row, right, the whole thing. And then the only tricky thing is that what I'm supposed to do is take this bottom piece here, B as a passenger, and I'm supposed to get something with indices just created by putting this into here. The first index here is the thing that became B. So the first index here is the thing that should now become A because I'm differentiating. That's the A is recording that. So what I should do is put minus, and then the B index, the B is a passenger, the C index should become A, right? And the D index is the thing that I've not mentioned yet, C, that's just going along. Okay, so that's exactly what you do if you think clearly about what indices mean what. That's what you get in the first line. And in the second line, that's easy. You just get derivative of CD. Remember, this is all in R3. These are just coordinate derivatives. Right, so what happens if you take the skew part in A and B? When I compute the curvature, what I'm supposed to do is to take this thing, and I'm reversing the roles of C and of A and B, applying it to the same gadget. What's going to happen? Well, actually, you can see that this expression here, first of all, there's let me just, is equal to. So, first of all, what you get is minus, maybe I'll just do one more step before I continue. Equals, right, derivative A, derivative B, sigma. And then there's this, which is just minus A of mu B sigma minus this thing, B of mu AC. And finally, down here, there's something which I'll just rewrite, but nothing's happening down there. Okay, so when you look at this, you notice that these extra terms that have appeared here by by dint of this connection, just putting whatever's there up there and then putting out whatever's there back up here, they're symmetric in A and B. This thing here and this thing here are exactly the same expressions. The only difference is that A and B are in that order, and here it's B and A instead. So even if we weren't dealing with something as nice as coordinate derivative here, this thing here would vanish if you take the skew part. Right? That's what I'm doing here. I'm taking the skew part. So there's no contribution at all from that. But because we're in flat space, there's no contribution at all from here either. And there's no contribution from here either. The whole thing, you get 0 plus 0 and 0. Right? The whole thing is actually 0. So the curvature here is 0. And that's the best of all possible connections. Right? It's a so-called flat connection. So if I just go back to this general statement, if you started with the de Rham complex and you did something rather trivial to it, so here's the de Rham complex, and so on, and all you did is instead of looking at ordinary everyday forms, so functions, one forms, two forms, and so on, if you just say they have values in some other vector space, like r to the k, right? So right, then that's just like k copies of the original de Rham complex. So anything you can say about the original de Rham complex is true of this. It's locally exact. Right, locally exact. Right, but if you try this in general, it's not locally exact. The reason it's not locally exact is because of this curvature. So if this were a vector bundle instead of just a trivial bundle like this, you get something which, even at the first stage here, the composition is curvature, right, by definition. But the really good thing is that curvature is exactly what you need in order to conclude if the curvature is 0. Curvature 0 is a flat connection. Curvature 0 terminology is it's a flat connection. And a flat connection is one which, even though you might not be able to do this explicitly now, in this particular case you can just change coordinates to make it look exactly like this. But even if you couldn't, curvature being 0 exactly characterizes the connections which, if you choose the trivialization of the bundle right, correctly, you get something which just looks like that, and it's locally exact. Okay? So a flat connection, the coupled de Rham complex, is locally exact. It's every bit as good as if you just had a trivial bundle there. And here we've got one of these things. All right, so now I'm going to draw a big diagram and do some diagram chasing, and some magic will occur. All right, so, okay, so get ready. So without going into any details at all about the operators themselves involved, right, we're just going to look at this bundle, E. In this particular case, one forms direct sum, two forms on R3. This is all happening on R3. Right, and we will, because of my observation about flat bundles being every bit as good as trivial bundles, right, we've got this coupled de Rham sequence, which is actually a complex. And remember, I'm just schematically writing all this like this. One forms tensor E, two forms tensor E. And because we're in 3 dimensions, once you've got to 3 forms, it stops. And there is no more. Right. Now remember that E is secretly 1 forms plus 2 forms. And so what I'm going to do is going to write down going to be a bit fancy about this and say that E you can project onto the one forms and you can include the onto the one forms and you can include the two forms. All right, so the fancy way of saying this is that this thing here is a short exact sequence. So what people tend to do is put a 0 here and a 0 down there and say that this is an exact sequence. What it means is that this one is injective, its kernel is equal to 0, and this one is surjective, its co-kernel is equal to 0. All right, okay. Already, because E has rank 6, and because this is a, well, I mean, this is our reason for actually creating this connection in the first place. We actually know what this kernel of the first one actually looks like. This is what replaces just R for the de Rham complex. It consists of pairs of a translation vector and a rotation vector. So this is my dimension 6 finite dimensional vector space, which is stuck at the front. This thing here is a bundle of rank 6. This has rank 6. So here you've got a three-dimensional subbundle, here you've got a three-dimensional quotient, and it's rank 6. This one is a vector space of dimension 6. This is what always happens for a flat connection. You always get the solution space of the first operator is always a vector space of the same dimension as the rank of the bundle.
Do you look this vector space?
We had this vector
As a trivial bundle?
where you can, right, okay, so it's strictly, okay, right, okay, yes. So strictly speaking, you can also think of this thing, in order to make precise nice, clean sense of all this, right, then this thing here should be, I mean, it's best to think of these things as actually sheaves. This is a locally constant sheaf. This is just a sheaf of germs of sections of E. Okay. Then it makes sense to actually write these things down as sheaves. These are sheaf homomorphisms and so on. But I'm being a little bit more informal. Right? It's just a vector space, rank 6 bundle. Okay, okay, right. This thing here, as a consequence, of this, if you just take the one forms tensor E, it's projecting to one forms tensor one forms. Right, so what I'm going to do is just write one forms tensor, whatever I had before, one forms tensor two forms here. All right. Next thing along, I just get two forms tensor everything. So here I get two forms tensor one forms, and here I get two forms tensor two forms. And here, what do we got? Three forms tensor one forms, and three forms tensor two forms. Okay, so far nothing exciting has happened. Except that now, if you figure out what, and these are differential operators going all the way along, as usual, everything's called nabla. And it's locally surjective at the end. Right, but now something exciting really does happen. Okay, so if you look at what this well, first of all, okay, the really exciting thing, there's several exciting things that happen. The really exciting thing that happens is that if you look at, well, any of these homomorphisms which go like that, across one and up one, including, for example, taking this, two forms tensor one forms, into this, across by this connection and up, you'll find that all of these things are actually just homomorphisms. They're not differential operators at all. I'll tell you what this one is actually is. Most of these things are fairly trivial, but this one here is slightly non-trivial. So I'm going to write down formulae for all of the red operators. And you can deduce these formulae from the basic formula. Right? It's nothing terribly difficult here. You're just working out what these various formulae say. Okay. This one is just inclusion. This one's simple. It's just taking the skew two forms and just including them into general two forms, like that. Right. This one is the most interesting one, as I said, and this one here is surjective. So let's just make a note of that. I won't tell you a formula for it, but it is surjective. This one's an inclusion, that one's surjective. This one is an isomorphism, but it's not the obvious isomorphism that you're thinking of. After all, these two bundles have the same rank. And at this stage, by the way, you can do this in any dimension. There's nothing special about 3 dimensions. It's only special about how it terminates over here. But as far as going up to 2 forms, this works in any dimension. This thing is an isomorphism. I'll just tell you what it is. You're starting with something in here. Let's call it phi. So it's got 3 indices on it, A, B, and C. Right, so one of them is saying it's a 1 form. And then you've got a couple of 2 form indices on it as well, B and C. So what you're really saying is you have a tensor with 3 indices on it. And it has the property that it's skew in its last 2 indices. Like that. And what you're getting from it is something which is, I've written the indices in exactly the same order, actually. And what you're getting from it is that this thing is mapped to, when you take the skew part with respect to the other 2 indices. Right. That's what this is. It's taking this, which is skew in its second 2 indices, and you're taking the skew part in the first 2 indices. In other words, exactly this thing minus the thing with the B and A interchange divided by 2. And I claim that that's an isomorphism. And for those of you who are familiar with Riemannian differential geometry, you'll notice that this is the, and there's a reason for this, this is the fundamental fact that you need in order to construct the Levi-Civita connection. So we're sort of coming back full circle to using the algebra that you encounter in constructing Riemannian differential geometry is somehow being forced on you by this diagram. So that's why it's really exciting. To prove that this is an isomorphism requires a small amount of work, and that's exercise 5 of the sheet, the exercise sheet, which has now been renamed. So it used to be Simple Exercise 2, but it's now Simple Exercise 2-3 because I didn't get far enough yesterday. But anyway, this is an exercise to prove this isomorphism. Now let's just see, and then we'll go into a slightly new topic. Let's just see how this gives you this very exciting Saint-Venant complex, just by staring at this diagram. So now I'm going to do what's called diagram chasing. It means you stare at a diagram and you think to yourself. Now, if you try and write this down, everybody gets terribly, terribly confused. So the only thing you can do is either do it yourself or watch someone explain it on the blackboard or whiteboard. Okay, so what does this diagram give to you? Well, first of all, it gives you, it's encoding, I claim, it's encoding this differential operator which we were actually interested in, namely the operator which takes, let's say, sigma b to this symmetric derivative. Right? The reason is that this is where sigma b starts. This is where it lives. Right? You may choose from here. You may choose actually any element in E, which maps down to sigma. For example, you could take mu to be 0. But let's take a general mu. right? Where do you actually end up? Suppose you just take a general element here and see what happens if you take this general pair over to here, but you're going to quotient by this freedom. What I'm going to do is I'm going to take this bundle here, which is included in that bundle there, and I'm going to just sort of cancel it out from the diagram. So I'm going to replace this with 1 forms tensor 1 forms modulo the skew forms. Right? And you think about what's really going on in terms of differential operator, in terms of these actual formulae that I'm giving to you. And what you're supposed to do is take the derivative of sigma and then ignore the skew part. In other words, you're supposed to do this. You're supposed to take the symmetric part. That's exactly what comes out of this diagram when you chase it. Right, so you end up with this, which is the same as, to use a bit of a fancy notation, it's the same as the symmetric tensor product of the 1 forms with itself. Okay, that's what you end. At the next stage, remarkably, you get complete cancellation between part of what you have here and part of what you have over there. This entire bundle here is cancels with this by dint of this slightly complicated algebraic isomorphism. But it's a linear homomorphism between these bundles. They just cancel. It just goes. Right? And here what you have is, well, 2 forms, tensor 2 forms, subject to being in the kernel of this. And that's the same, actually, you can check in 3 dimensions. That's the same as having, you can identify the result as being symmetric 1 forms again, if you like. More exotically, what you can do is identify this, the kernel of this, as being exactly tensors with Riemann tensor symmetries. This thing here has 2 pairs of skew indices, and this is the so-called Bianchi symmetry. So, and it just so happens in 3 dimensions, you can simplify things and write the result as symmetric 1 forms. And then here at the end, you have, well, 3 forms, pretty much the same as the trivial bundle in three dimensions, and 2 forms are pretty much the same as 1 forms in 3 dimensions. And lo and behold, you notice you've created exactly the bundles that you were expecting in the Saint-Venant complex. You've got 1 forms, just vector fields. You've got symmetric 2 forms here. You've got symmetric 2 forms here. And here you've got just vector fields again. And these things acquire differential operators between them. And this one here is the killing operator. This one here is taking the divergence. Everybody will believe that. But this more complicated operator going between here. So when you start doing diagram chases, you use a lot of... and here is actually a bit more complicated, because what you really do is you take something in here. You pick an arbitrary something in here which maps to it. You map the whole thing across. Then you say, but look, this is an isomorphism here. So you can arrange that this be 0 by choosing a particular lift here from here to here. But when you do that, you're using 1 derivative, because there's a derivative involved in constructing this. Okay, 1 derivative has been involved. And then you say, look, if you make that special choice, start here, lift, go across. It ends up in here. Therefore, it goes to 0 in here, and therefore it's actually secretly in there. And that's another derivative. That's why the differential operator between here and here is 2nd order. That's why it's curl. Right, so then this is something you just have to do for yourselves and see. Right? We'll have a... This is a part of a theme where you start writing down natural complexes of differential operators, and then you start doing some diagram chasing. This is diagram chasing in order to get something which is much different and actually simpler than what you started with. Right? And here is the best example. In other words, the simplest example, which is one that doesn't involve connections at all, is to do with contact geometry. So here we've got a new topic. I'll just mention the key words, and then we'll stop. This is contact geometry or contact manifolds. Contact manifolds. Contact geometry is the sort of local name for it. A manifold with a local contact geometrical structure is called a contact manifold. Right, so this is, at first, looks like a different topic. So let me tell you what a contact manifold is. And first of all, I'm just going to relate it straight away to what Francine has been talking about in her talk on hypersurface CR geometry. So and I'll keep the dimensions the same as far as I can. A contact manifold is a 2n plus 1 dimensional manifold. It's an odd dimensional manifold. Right. And the structure that you have on here is a very, very simple structure. It's much simpler than a Riemannian metric or something like that. What you have is a subbundle. Let me call it H. H for hyperplane, or H for hyperplane, a subbundle of the tangent bundle to M. Right, and this one has dimension, rank 2n. Right, so this is an even dimensional bundle. Subject to some non-degeneracy condition. Right, subject to some non-degeneracy. Right, and this is what a contact manifold is. There are three key examples that I'd like to just mention before we stop. One of them, example number 2, is exactly what Francine has been talking about, where M might be given to you as a real hypersurface inside Cn plus 1. Right, now remember our viewpoint last time of what a complex manifold is, what this is that there's an endomorphism of the tangent bundle here. So you can take the tangent bundle of M, which sits as a subbundle inside the tangent bundle of Cn plus 1, and you can apply J to it and look at how, so J is multiplication by I, but thought of in a real way, and you can look at the intersection between M, the tangent bundle to M, and J times the tangent bundle to M. And this will have rank, even rank, rank 2n. This will be H, and it will sit inside the tangent bundle of M. Right, and H is the thing which is spanned, at least this complexification is spanned by d by dz's and d by dz bars in Francine's course. Okay, that's one of the examples of a contact manifold. Another one is actually from question 2 of the first exercises. And another one is that instead of looking at this as your basic complex manifold, nobody has actually mentioned so far a manifold other than a domain in Cn.
Sorry, G is the complex structure? G.
Right, so J is the complex structure. Okay. J is the complex structure, yeah. And when I've done this, I've just forgotten about the complex structure. I do this, and I forget where it came from. It's contact structure. And example number 3 is, well, here's a more exotic complex manifold, CP2. Right? And CP2 is good because it has a good symmetry group, but in particular, you can I'll explain a bit more about how this works. You can let this particular group act on CP2, and it has 3 orbits when you do that. And one of them is the 3-sphere sitting inside CP2. This is a codimension 1, so in other words, a real hypersurface, a smooth real hypersurface inside a complex manifold. It acquires a CR structure. It's a hypersurface CR structure, but it's on a compact manifold rather than just locally. So this is a much more sort of cool example And this has to do with, Poincaré's observation that the ball and the polydisk are not biholomorphically equivalent, as mentioned by Raphael and Giuseppe. Right, so these contact structures are connected with what we've been looking at so far. More next time.